So in this video, we'll learn about the bus, specifically the system bus, right? So again, we have referred to this term earlier. A bus is basically a collection. A bus is simply a collection of wires, electronic wires or lines. So on these lines, you can either send addresses, you can send data, you can send control signals, whatever you want, right? So a bus is basically a collection of electronic lines, right? So literally wires that you connect. A set of them or a collection of them is called a bus. So now we'll talk about something called as a system bus, which is what we want to focus on this whole discussion, especially this video. Now if you think about it, look at this. This is your CPU, this is your main memory. This is your input-output devices, right? There could be multiple input-output devices. For example, you could have a monitor. Okay, a monitor is an output device. You could have a keyboard, which is an input device, right? You could have a printer, which is an output device. You could have a mouse, which is an input device. So you could have multiple input-output devices connected to the same computer, right? Now, if you think about this, see, if you think of this as collection of lots of lines, okay, you can think of your system bus as a collection of lots of lines. The system bus specifically connects all of the major components on your system or on your computer system, right? Of course, what are the most important components? Your CPU, your main memory, and the I/O devices. So the system bus actually in the physical world, this system bus is actually present on your motherboard, right? It is part of the motherboard printed circuit board, or it's part of the motherboard chip itself, right? So the system bus plays a very, very important role because it is used as a highway or a channel. Literally, it's used as a highway through which CPU communicates to memory, CPU communicates to I/O, I/O also communicates to memory, and all of these cases, right? Your system bus itself consists of three types of lines. There is obviously address lines. Remember that address lines are always outgoing. Okay, from the CPU, they always outgo towards the memory or towards I/O devices, right? Remember, just like the way we had, look at this, we saw this, right? We saw CPU interfacing with memory, right? We saw CPU interfacing with memory, right? We had address lines, we had data lines, right? Data lines are both directional, address lines are one directional. We also had control signals like read, write, all of that stuff. Just like the way CPU talks to memory, CPU also has to talk to I/O devices. Look at this, CPU also has to talk to I/O devices, right? Wherever I'm moving my mouse, all of that data has to be sent to the CPU for CPU to process that information, right? Just like the way we have seen CPU memory interfacing, there is CPU I/O interfacing also. We have to interface the CPU to I/O also. And what does I/O devices do? Again, remember, your hard disk is also an I/O device. Your hard disk is also an I/O device. So the way it works is your CPU needs to access data from your I/O devices also, right? So your system bus is literally like one highway of wires through which your CPU is connected to I/O, your CPU is connected to memory, your memory is connected to I/O. All possible connections are possible here. Even to address, for example, even to address or obtain data from a keyboard, from a disk, from a monitor, to write data to a monitor, to output data to a printer, to input data from a mouse, it still works just like your memory. Every device has an address associated with it. Look at this. The way it works is your monitor could have some address associated with it. Just like the way memory cells have addresses. Your monitor will have an address and the CPU will keep sending some data to the monitor. It will only write data to the monitor because monitor is an output data. Similarly, your keyboard will keep giving inputs. Your keyboard also will have an address associated with it, just like your memory addresses. So just like the way CPU memory interfacing works, similarly CPU I/O interfacing also works, right? CPU I/O interfacing also works. Of course, address lines are only outgoing. Your control lines can be incoming or outgoing, right? Similarly, your CPU, your data lines are bidirectional. You can send data to the I/O device or you can obtain the data from the I/O device, right? So again, your system bus is literally one set of wiring or one collection of wires that connects your CPU to I/O, I/O to memory, and CPU to I/O. But very importantly, remember that CPU works very fast because its clock speed is very high. Memory works fast but not very fast. Your I/O devices are actually very slow, relatively speaking. Look at the rate at which you type on a keyboard. It's just a few keystrokes a minute, right? Even the rate at which your monitor works, it's just a few hertz, right? If you look at the refresh rate of your monitor, monitors have 60 hertz refresh rates, which means the monitor screen is refreshed once every 60 seconds. Once 60 times every second. Look at your CPU speed. Your CPU operates at 2 gigahertz like speeds. Your memory works at 1 gigahertz like speeds, right? Your IO devices work very, very slow. Even your mouse also works very slow as compared to your CPU and memory, right? So there is a lot of speed issues here, and we have to keep that in mind while designing our architectures. Very, very importantly, right? Your system bus itself will contain address lines, because whether you want to address a memory location or you want to address an IO device, you need address lines to say which memory location you want if you're addressing a memory cell, or which IO device you want to read data from or write data to. Similarly, you have data lines. Address lines are unidirectional. Address lines are always going out. So address lines go from CPU to the IO device or CPU to the memory device, right? Similarly, you have data lines. The data lines are bidirectional. Data lines are bidirectional, which means you can write data from CPU to memory. You can read data from memory to CPU. You can write data from CPU to IO. You can read data from IO to CPU. Both directions is possible. Then you have control lines. Look at this. What are control lines? For our memory, we saw read, write, right? We saw read, write. All of them are control lines, which tell you what this memory chip should do. Similarly, your IO chips or IO devices also have control lines. In the case of CPU IO control lines, you have, look at this, what you have here is this. What you have here is these lines from CPU to IO could go from CPU towards IO, could go from CPU towards IO, or they could also go from IO to CPU. They could also go from IO to CPU, right? So these are either in this direction or in this direction. So the control signals are also, see, each line is unidirectional, but the control lines together, some of them go from CPU to IO, some of them go from IO to CPU. Now you might ask, why do I want my control signals to go from IO to CPU? Because there is a concept called as interrupts. Okay, we'll learn about this in much more detail later. But what interrupts do is, imagine I have a printer. Okay, let's take this simple example, right? Imagine I have a printer. Okay, the printer is printing something. The paper, it ran out of paper, let's say. It ran out of paper, there is no paper on the printer. Then it has to send the signal to the CPU, informing the CPU that, sorry, I'm not able to print, I have an error or I have a problem. How does it transmit that information? It is connected to a control line or a control signal. It sends a control back to the CPU saying, sorry, I'm not able to print, please interrupt this process right now and tell the user or tell the end user of the computer to put in some paper so that I can continue printing, right? So that's a very simple use case of how interrupts works. Again, interrupts is a very big concept. Again, this is a concept that we also study in operating systems in lots of detail. We'll study interrupts to their full depth when through the rest of this course. But what I gave you is a simple intuition on why IO devices wants to send signals to CPU also. Right, so the control signals, the CPU can send signals to IO, like your read write, right? Your CPU could say, oh, read the data from the keyboard or write the data to the monitor. So you will have read write type of signals that the CPU sends to IO devices. IO devices also send to your CPU signals like, sorry, I ran out of paper, or I have a problem, I'm not able to show what you have done, right? All of those things also, some IO devices, not all IO devices, could send signals back to the CPU also. Right? So your system bus broadly consists of address lines, data lines, and control lines. And this is how everything is connected through the system bus. But here comes one simple problem. Look at this. There is one very simple problem that occurs, which is called the ambiguity problem. The problem arises as follows. So imagine if your CPU, let's take a simple example, right? Suppose if your CPU says the address, CPU places an address. Let's say my address is 4 bits, just for simplicity. Let's say my address is 4 bits. Let's say it puts this address on the address lines. Okay. Now it says, now let's say it puts this address and it wants to read the data. Okay. So these are my data lines now. Okay. So this is my data line. Okay, so this is my data line. My CPU now, what the CPU is doing is on the address it is placing 1011. Data lines it says I want to read. So in the control signals, so on the control signals it says read equals to 1. Okay, that's what the CPU is sending. Now look at this. These wires are connected both to memory and to IO devices, right? So now what happens? Now let's see what happens here. Now look at this. Okay, let me explain you how this works, right? So this address 1011. So in your memory at 1011, whatever data is there, because the read is also set to 1, we'll start reading the data, right? That's one possibility. Imagine my keyboard address is also 1011. Imagine my keyboard address is also 1011, right? Because my IO devices are also connected to the same address lines. This is my whole system bus, right? My whole system bus is connected to both IO devices and to memory. So this address, now look at this. This address goes to your RAM. The same address, all these 3 signals, the same address could also go to your IO devices. Let's assume this IO device 1011 corresponds to a printer. Now what happens now? Whatever data is stored in your 1011 memory location is copied onto the data bus. But whatever data the keyboard wants to send is also copied onto the data bus. Now there is an ambiguity or confusion or dilemma or doubt on which of these 2 data has to be sent to the CPU. Is the CPU referring to the memory address 1011 or the IO address 1011? That's the confusion. That's the ambiguity. So having a system bus like this causes problems. While this is an efficient use of your wires. Look at this. More the wiring, the worse and harder the motherboard design is. And more the wiring, the more is the electricity required, the more cumbersome it is to design your printed circuit board for the motherboard. So it's very good to have fewer wires that connect your CPU to memory, your CPU to IO, and your IO to memory. It's a good idea. But the problem is the moment you have this type of configuration, you will run into problems like this. Whenever the CPU says my address is 1011 and I want to read, these 2 systems don't know which of these 2 systems it's referring to. Is it referring to the RAM address or is it referring to the IO address? Because my IO address 1011 is connected to the printer. Now both the RAM and the printer will place the data on your data bus or data lines. Now which of these data will be taken up by the CPU? There is a lot of confusion there. So this is called the ambiguity problem. Now to avoid the ambiguity problem, there are multiple configurations which will avoid this partially, if not fully, right? So and that's very, very important aspect of designing a proper system bus. The first configuration is called a configuration in which we have something called as an IO processor. There are 3 popular configurations, right? So this is called as in this configuration we have something called as an IO processor which helps us resolve some of the problems. Let's see how it works. This is the block diagram again. This is my system bus, this is my CPU, this is my memory. Okay, my whole system bus is here, right? Instead of drawing it like a thick wire, I've drawn it like a thin wire just for simplicity. Now what I have here is a special purpose processor called as an IO processor. Remember, your IO processor is a special purpose processor. This is a special purpose processor which is designed to handle all IO devices. So this IO processor is connected to IO bus. To this IO bus, all of your devices are connected, whether it's your printer, whether it's your disk, whether it's your keyboard, whether it's your mouse, whether it's your monitor, right? So all of these devices are connected to the IO bus. So what do we have now? We have different buses here. The system bus is connected just to memory and the IO processor only. So the system bus is connected only to memory and IO processor. For the all the IO devices are connected to the IO processor. Again, this is a special purpose microprocessor. This is a special purpose microprocessor. Actually, this sort of setup is used in very advanced systems, in high performance systems. This sort of setup is used in high performance computing systems. Like your high-end servers and all use this sort of setup, right? Regular systems do not use this a lot because you're having a new, in addition to your central processing unit, you have a special purpose microprocessor just for IO, which will make the whole setup expensive, right? That's one of the problems. This could be a full-fledged microprocessor with some registers in it. This could be a very complex microprocessor onto itself. but it's a specially designed microprocessor to handle all of your IO stuff, right? So again, this is expensive. This is used in high performing systems or high performance systems. It's expensive, but the way the whole thing works is this. Look at this. So from my CPU, look at this, my control signals, whatever control signals come. See, my system bus consists of 3 types of wires, right? Control signals, address signals, and data signals, right? Now the way it works is this. Look at this. My CPU is connected to both my IO processor and memory. All my IO devices are connected to this, right? The control signals are common both for memory and IO. See, if I want to read, the same read signal is connected both to the IO devices. The same read signal is connected to the memory signals. Now the read signal is not sent directly to the devices. It is sent to the IO processor, right? So the control signals are common in this configuration. The address space is also common, which means I could have a memory location which is 1011. I could also have a, let's say, I could also have a printer whose address is 1011. Okay, that's what it means when it says common address space. Common address space corresponds to common address lines also. So the same address lines in the system bus go to memory, they also go to IO processor, right? The most important thing is the CPU basically says at any point whether my memory is active or my IO processor is active. It will pick only one of them. See, let's assume the CPU sends exactly the same case like earlier, right? Imagine my CPU sends address 1011 and it wants data input. If it wants data input, and let's say it says read equals to 1. Okay, so let me write this carefully. So it says data and it says, read equals to 1. Let's assume it says this. Now this same address goes to memory. This same address goes to the IO processor. So 1011 address corresponds to the printer. This 1011 corresponds to this memory location. It says read. The read signal goes, because same control signal, same common address space. So the same read signal goes to this, the same read signal goes to this. Now the CPU says whether I want to read from IO or I want to read from memory. There is a special line that it says. If that line is also connected to the memory, right? So there is a special control line in this case which says, do you want to read from memory or do you want to read from the IO processor? Very simple concept here, right? So it can either read, say this, if its value is, let's say 1, probably it reads from IO processor. If its value equals to 0, it will read from memory. Now the IO processor will now decide, okay, because it's the same address, right? Now the IO processor will say, which of my devices has the address 1011? Okay, suppose there is a special line. There is one special line which says, this special line will say whether you want IO or memory. So this line will most likely look like this, I/M bar, which means if it is 1, see this line is connected both to your IO processor. This line is also connected to your memory. If this is 1, your IO chip is active. Then we'll get data from the 1011 device, which is the printer connected to my IO processor. If this is set to 0, then the IO processor does not become active. My memory chip becomes active. Right? So there will be one special line here which says which of these 2 chips is active or which of these 2 components is active. The moment you have your IO processor active, now it will pick one of, so when IO processor is active, memory is inactive. When memory is active, IO processor is inactive. Okay, that sort of setup is done between CPU, IO processor and memory. So you have common control signals, you have common address space, right? You have this, right? Now, but you have different buses. You have one bus for all of the IO devices. You have one bus for all the system. You have one bus for memory and IO processor. But there is one major advantage which comes with this, which is there is a direct access between IO and memory. So just like your CPU can read and write data from memory, remember your IO processor is also a processor. This is also a processor. So imagine if I want to store some data from, let's say, from my suppose from my keyboard. My keyboard is sending some data. Suppose I want to store that directly to memory, right? Suppose if I want to directly store that to memory. Now there will be special lines between your memory and IO processor also. What they do now is it says, so this IO processor, remember, it's at the end of the day, it's also a microprocessor. It's just a special purpose microprocessor. So in this setup, I can have direct line between my keyboard, like a device like keyboard, whatever data the keyboard is sending, it can directly store in the memory without going through CPU and then to memory. right? So one of the big advantages of this type of setup is IO memory direct access is possible. So directly I can store data from my IO devices to the main memory, which is very, very helpful, which is super duper helpful, right? Because remember, my CPU, instead of copying it directly from, let's say, my keyboard to memory, the other alternative is take it from keyboard, send it to CPU, the CPU now sends it to memory. Instead of having these two paths, directly I can store it into the memory. So I have a IO to memory direct access, which is very, very beneficial, especially to store data that these IO devices are sending. Because the CPU could be using that time to run some other process, right? To run some other program. Without disturbing the CPU, whatever data the keyboard or mouse or anything is sending, we can directly store it to the memory, right? While CPU is performing some other task, right? Thereby obtaining better utilization of all the resources. Remember, your IO processor is a special purpose microprocessor. Today, high-end systems do have a special purpose IO processor to enable the communication between CPU, memory, IO devices to be much more efficient, right? But it's slightly more expensive because you have one more processor on your board, right? Okay. So the second concept, the second bus configuration is called as isolated IO. Very simple concept actually. First, let's understand the concept with this block diagram. Then we'll see how it can be implemented in an 8085 processor, right? Two parts. The first part here is this. Look at this. This is my CPU. Look at this. In my isolated IO, what I'll do is this. It's a very simple concept, right? So in my isolated IO, I have my address. My address line is common. Again, here what I've done here is, instead of drawing my system bus as just one line, I've broken up into three parts. The address lines, the data lines, the control lines. Okay, in isolated IO, what happens is the address lines are connected both to memory and IO devices. Okay, here I've drawn only one IO device, but I could have multiple IO devices here, right? I could have multiple IO devices here, right? This is IO device 1, this is IO device 2, so on and so forth, right? So the same address is given to both your memory and IO devices. The same data lines are connected both to your main memory and to your IO devices. The difference here is it's called isolated IO because the control signals are different for the main memory. The control signals are different for the IO. Right? So now let's see what happens. Look at this. Imagine if I give an address of 1011 and if I say read equals to 1. Right? My control signals, now I'll have to differentiate whether it's a memory read or an IO read. Okay, I need to differentiate. I just can't say read equals to 1. Now I have to say also whether it's a IO signal or a memory signal. I also have to explain whether it's an IO signal or a memory signal, right? Now let's assume I say my address is 1011. So the same address goes to your memory chip. The same address goes to your IO devices also. Let's assume this IO device address is 1011. This IO device address is also 1011, let's say. This memory address is also 1011, right? Now the read signal, if I give an IO read, what happens? Only this chip will be active. This memory will not be active because it's not getting any read signal, right? If I give IO signal plus, sorry, if I give, so my IO signals are typically, if you look at the 8085 processor, you have this chip, you have this pin number 34, which says IO/M bar. So if this pin is set to 1, this implies that what I'm giving is an IO control signal. If this value is 0, that implies what I'm giving here is a memory signal. So what I'll do now is, I'll take this IO by M bar and I'll take this read. I'll have my read somewhere, right? Where is my read? My read is barred. So read is active low. So what happens if this is 1 and my read equals to 0? Okay, if this is so, then what do I read? Then I do IO read here. Then I do IO read, which means I read from this chip now. I'm giving the same address 1011 is going, but because this IO/M is set to 1 and this IO by M bar is connected. So this IO by M bar line is connected both to your memory and to your IO, right? This line is connected to both memory and IO devices, right? Now when it is 1, what you will do is you'll read from the IO devices. When it is, suppose if this is 0, which means I want to read from memory because I have M bar here, right? If this is 0, this is equivalent to memory read. This is equivalent to memory read. So what in isolated IO, what we have here is we have isolated or different lines for memory control and IO control, logically speaking. We have the same address space, we have the same data lines, but we have different lines for memory control and for IO control. And this is how it works. Very, very ingenious solution. So the way it will work is this. My IO, if it is 1, then this IO devices, so this IO line, look at this. Internally, the way it will work is this. Okay, let me draw this with a different color. Okay, let me use this color. So this IO line will be connected to your memory chip. It will also be connected to your IO chips. It will be also connected to all of your IO chips. Right? When it is 1, these IO chips will be active. And the address of this IO device or IO chip is going to be different from the address of this IO device. Right? So each IO device has a unique address. Remember that. So the moment this is equal to 1, all of them will become active. When it is 0, I'll connect it to one of the pins to my memory, such that when it is equal to 0, only then this memory chip is active. Otherwise, it is dormant. Right? Very, very simple logic here. Right? So what I have here is I have my control signals in such a way that at any point, because my controls are isolated, this is called as an isolated IO bus configuration. And using an 8085 processor, there is a special line here. Again, here the chip enables us to do this isolated IO very easily, because it gives us this special line through which I can either activate my memory or I can activate all of my IO devices. Here, remember, here I don't require an IO processor here. I don't require an IO processor here. Right? Because if this value equals to 1, all of these IO chips are active and each of these chips will have one address. Or see, this could be an IO chip or it could be an IO device. At the end of the day, so I'll keep using these words interchangeably, because if you ever open your keyboard also has a bunch of chips. Right? So if you ever open your keyboard, right, you have bunch of keys. You type in these keys, this data goes to this IO chip, which is then connected to the system bus. Okay, so if you take your keyboard, right, if you ever open your keyboard, you have these mechanical keys. You press on that key, that signal is transmitted. There is a small electronic circuitry here or a chip, which is actually also called as the IO chip, not an IO processor. IO processor is a much more powerful thing. There is a small electronics chip here. It's a digital logic design chip here, mostly consisting of flip-flops, right? It stores this information, whatever I have typed, and it then sends it to your through your system bus, either to the CPU or to RAM. Right? This is how it works. But again, in this isolated IO configuration, your IO devices cannot communicate with memory directly. Unlike your IO processor based systems. Your IO processor based systems, your IO devices can directly communicate with memory, just like the way they communicate with CPU. In this setup, your memory and IO devices cannot talk to each other, because all the data from your IO devices have to pass through CPU. So if you want to get some data from this IO device and store it in memory, first it goes to the CPU, gets stored in the CPU register, then we copy that from the CPU register to the memory. Okay, so that's how it has to work here. The third thing is called as memory mapped IO configuration. Okay, this is also a very ingenious solution. So in memory mapped IO, the way it will work is this, right? This is also a very ingenious solution. Here, what I do here is this. Let's assume from my CPU, I have my address lines, my data lines, and my control lines. The same address lines, data lines, control lines are connected to my main memory. They're connected to my IO devices. This is, let's say, IO device 1. I could also have another IO device, right? I could have multiple IO devices, right? So this is my IO device 2, and so on and so forth. So same lines are connected to my main memory, to my IO devices also. Now, obviously, how do you solve the problem? There is a way we can solve the problem by actually doing something called as a shared address space. And for that, we will use decoders. Let's see how it actually works. So the way I'll solve the problem now is I'll say, look at this. I'll say all memory, I could say all memory addresses. Okay, let's assume my address is 4 bits. So let's assume my address is 4 bits, just for simplicity as an example. Okay. So let's assume my address is 4 bits. So I could say that whenever this value is 1, 1, okay, whenever the first 2 bits are 1, 1, it all corresponds to IO devices. Okay, I could say that. So what am I doing? If my address is 4 bits, what is the total addressable space? 2 power 4 addresses. The total addressable space is 2 power 4 addresses. But instead of having 2 power 4 addresses in the main memory itself, what I'll do now is I'll say 00 dash dash 10 dash dash 00 dash dash 11 dash dash. Okay. So in these dashes, you can either fill zeros or ones. So I'll say whenever my first 2 bits are 1 1, right? All these values correspond to IO devices addresses. All these correspond to IO device addresses. Okay, so I'll simply say all these correspond to IO device addresses. When these values are, when the first 2 bits are not 1 1, it corresponds to memory addresses. I'll state this. So what happens now is, internally what happens now is, whenever the address is 00 followed by anything, it will activate the main memory. When it is 1 1 followed by anything, it will activate the main memory and I'll get whatever is the data stored in that address. But whenever the first 2 bits are 1 1, the memory is deactivated, right? Only the IO devices will become active here. In this case, only the IO devices will become active here, right? And when the IO devices become active, look at this, when the IO devices become active, right? Then again, here I have 2 more bits. In 2 more bits, I can create 4 more devices, right? So the way it will work actually using a decoder is as follows. So let's actually draw a decoder here. So let's create a 4x16 decoder here because we have 4 bits addresses, right? So what happens is the address lines, look at this, the address lines are connected to the 4x16 decoder as inputs. So you have 16 outputs now. Look at this, you have 16 outputs. What is this number now? 2 power 0, 2 power 1, 2 power 2. So this is 4, 2 power 3, this is 8. So numbers from 12 up to 15. Look at this, numbers, address numbers from 12 to 15 should correspond to IO devices. Numbers from 0 to 11 should correspond to memory addresses. That's the core idea here, right? That's the core idea. So what I'll do, look at this, in my 4x16 decoder, I'll have 0, 1, 2, so on, so forth. Let's say 12 up to 16, up to 15, right? That's what my 4x16 decoder will have. So all these lines from 0 up to 11, okay, from 0 to 11. So let me draw this more clearly for you. So the way I'll design this is, I'll have lines like this. Okay, let me draw it clearly. Let's assume this is my 0 line, this is my line 11, this is my line 12, so on so forth, line 15. These 0 to 11, all these lines, if I'll pass them through an OR gate. If any of them is true, look at this, if any of them, which means if my input value, look at this, my address is 4 bits, right? My address is 4 bits. If the address that is sent to me lies between 0 to 11, then 0 to 11, one of these lines will be set to 1. So I'll pass them through an OR gate and I'll connect them to my memory chip. So now what will happen here? If my address lies between 0 to 11, then my memory chip will become active. Very simple. Otherwise, my memory chip will become inactive. This line 12, this 12, I'll connect it to IO device 1 like this. This 12, I'll connect it to IO device 1. So which means if my address is 1100, look at this. Let's assume my address is 1100. So what happens? Which of these 16 outputs will be active? Output 12 will be active. When output 12 is active, my IO device 1, whose address is 1100, is active. And my memory chip is now inactive. So even though we are sending the data, it is not addressing anything in the memory. It is now getting the data from the IO device 1. Similarly, this 13, this output 13, I'll connect it to my chip 2 or my IO device 2. Right? So this will correspond to address 11101. So on and so forth. I could have at most 4 IO devices here, right? Corresponding to pins 12, 13, 14, 15. So I could have up to 4 IO devices here. But my memory can only have values from 0 to 11. Even though my address is 4-bit. Look at this. What am I doing here? It's called memory mapped IO. And why is it called memory mapped? This whole method is called memory mapped IO. It's called memory mapped IO because we are breaking the whole address space into 2 parts. In this example, we have taken the address space from 0 to 11. This whole space, we are giving it to your memory. Address space from 12 to 15, we are giving it to IO devices. Which means the whole memory, in the memory mapped IO, the whole address space is broken up between your memory and IO devices. Okay, and again, here we are using a decoder to do all of this logic here. Very simple concept, right? So memory mapped IO is also a very, very popular strategy, but just like in the previous case of isolated IO, you can't communicate directly between your IO devices and main memory here, the way you can with your IO processor. Again, IO processor is used in high performance systems. If you buy high-end graphics cards, look at this. Actually, if you buy a graphics card, you can think of the graphics card. Some of you who play games, right? You may have a high-end graphics card from NVIDIA or companies like that. You can think of the NVIDIA graphics card as an IO processor, which is connected to your monitor, right? Because it has to update graphics very, very fast on your high-end monitors. So you can think of it as one type of IO processor, but it's a specialized IO processor connected only to the monitor. The general purpose IO processors are connected to all the IO devices, not just to one device, right? So again, on modern systems, there are multiple processors. CPU is just one of the processors. You could have a graphics processor, you could have an IO processor that is connected to all the IO devices, etc. But of course, this has the advantage that I can talk from IO device to main memory directly. While in this case of memory mapped IO and also in isolated IO, my IO devices cannot directly talk to memory. But here again, look at this. What is the trade-off in memory mapped IO? My effective memory size is reducing, but I'm also able to accommodate IO devices with minimal change. With almost negligible change, everything will work here, right? Let's solve a simple problem now. Imagine I have a microprocessor that supports 128 mega words of memory. Okay, so what is 128 mega? 128 is 2 power 7. What is mega? 2 power 10. So 2 power 20. Mega is 2 power 20, right? So 2 power 27 words of memory, which means the address is 27 bits. Okay, first data point. Now in this system, they are using a memory mapped IO. Just like this, they are using a memory mapped IO. Now in the memory mapped IO, they are saying that if the three most significant bits, MSB, this is a term that you may have learnt in digital logic circuits. MSB basically means most significant bits. So you have 27 bits, right? You have 27 bits, right? So on and so forth, 27 bits. This is your 27th bit, 26th bit, 25th bit, 24th bit, 23rd bit, first bit. You have 27 bit addresses, right? If the first 3 bits are set to 1, they're assigned to IO ports or devices. Whenever you hear this term port is basically where something is connected to. Think about it as a connection point. Port is nothing but a connection point. So whenever these 3 are there, this corresponds to IO, right? Whenever these 3 are not equals to 0, it corresponds to memory. Exactly similar here. Even here, that's the example that I've taken, right? If both of them are equals to 1, then they're connected to IO devices. If they're not equals to 1, they're connected to memory devices, right? Now the question here is, how many IO addresses do we have and how many memory addresses do we have? Very simple question here, right? So let's see. So if all 3 of them are set to 1, right? How many IO addresses are there? You still have 24 bits that are left. You still have 24 bits. In 24 bits, you can have 2 power 24 addresses, right? So the total number of IO addresses is 2 power 24. You can connect 2 power 24 IO devices to this system. How many memory addresses are there? Look at this. Except for 111, how many other combinations are possible? For these first 3 bits, apart from 111, right? How many other, see how many possibilities are there for 3 bits, 2 power 3 possibilities? 2 power 3 is 8 possibilities you have. Out of these 8 possibilities, 1 possibility is assigned to IO devices, which means you're left with 7 other possibilities for these first 3 bits. 7 other possibilities, right? Ranging from 000 up to 110. If you enumerate them, you'll get 7 options. So the first 3 bits can take 7 out of the 8 values. The next 24 bits can take 2 power 24 values. So the total addressable memory, the memory addresses that you can have is 7 into 2 power 24. Very simple question here, right? Here, they've just not given you the number of bits in the address clearly. They've told you the microprocessor can have at most this much memory, or it supports 128 megawords of memory. So they've given this. From this, we can easily compute the number of address bits. Given the number of address bits and given that the three most significant bits have to be 1, it's very easy to compute the number of IO addresses and memory addresses. Very simple question.